Thank you, David. Kira, everyone. Thanks for coming for my talk. I choose the title which strongly supports my journey from my undergraduate to where I am currently. I just want to run through some basics which has been discovered 150 years ago. As you recall in your textbooks, J.J. Thomson discovered the electron. That led into the budding model. Then our New Zealand-born Rutherford, Marston, Geiger, Miller did a famous experiment of cold foil experiment, which resulted the atomic nuclei. Subsequently, discovery of proton, and that developed a Rutherford Bohr model. Then Schrödinger, who came up with the equation based on quantum mechanical theory, which describing the electrons, the whole nuclear structure. Believe it or not, atoms and electrons can be manipulated the way you like. That leads to the whole discovery of technology, what we currently use. So that's the fundamental physics which has been done 150 years ago. So what is ion? Atoms are neutral, they are not charged. But when you strip the electrons, they have become ion. That's what we call ion beam. So ions are atoms which are less or more electrons and protons. And that's what I learned during my undergraduate. But that made me to join Department of Atomic Energy back in India as a PhD student, where I played with this nucleus and atom and to understand what else you can do. Then I joined GNS in 2001, where GNS have a 3 million volt 1 degree generator, which is paired in the Grace field, which has been commissioned at early days, and where we have been playing with quite a bit of nuclear instrumentation. But the challenge is ions cannot travel in the air far because they are extremely reactive. So you need to come up with a way of remove the gas molecules so the ions can travel in air. That means you need extremely high vacuum. Assume that you need a pressure 1 billion times less than atmospheric pressure. So this is why ions are always travels in by high vacuum conditions. So when I joined GNS, my first task, we got 3 people who were trying to transform the nuclear sciences to modern days applications. So what we did, the first thing is we looked at it, what happens when ion beam hits any matter. Then we used the nuclear physics, explained there is a X-rays generator, there is a gamma rays are coming through, some ions can come back scatter back, some extra nuclear reactions taken. So which enabled us to come up with a various analytical technique for many applications. One of the key applications which made significant impact in New Zealand is looking at the air quality. So if we look at the spectrum on the right side, which is called particle-induced X-ray emission spectrum, which detects what is in our air every day we breathe. By looking at the elemental compositions and how much is there, you can identify the source of any contaminations. And that has been heavily used by the air quality management in New Zealand. Every regional council uses this fantastic facility to monitor the air quality, and we actually expanded into Southeast Asia, even globally. So one of the few examples where we can demonstrate how we apply the Rutherford discovery to environmental applications. We also did a lot of biological applications and water as well. Then I was thinking, right, what else we can do new? I was always curious on what happens when ions interact with the materials, because as I said, they're charged. So we know that when ion beam interact with the material top surface, let's say nanometer, micrometer, it's fantastic to modify the surface to create a new functionality. It can be a new composition, it can be a new crystal structure, it could be a nanostructure. So we understood better the basics of how ion interacts with the matter. Then we looked at it, how can we apply for New Zealand interest? So I had a privilege to join New Zealand Product Accelerator, which connected to more than 250 companies in New Zealand. So we looked at, okay, can we really do something for New Zealand? The first science what we did is we developed ion magnetic nanoparticles in a glass, just a piece of glass, which actually able to detect the hemoglobin content of the body. So we commercialized through New Zealand company for security applications. Then we continued our journey. Then we looked at it, can we do something for energy? So one of the basic, good thing in the physics is there is something called thermoelectric materials, which can be used to convert the heat into electrical voltage. So we did some work on coming up with the new materials, let's say copper iodide, which is low cost, modifying the crystal structure and tailoring the composition so that we can improve the efficiency of the thermoelectric materials, which lead into another commercial product as well. Then we looked at a bit more deeper on energy, and when this big challenge about the 5G communication, 6G communication, a lot of semiconductor people approached me. At the moment, if you happen to look at your Wi-Fi router, inside the hardware, there is a filter. So those filters those days can only filter up to 5 megahertz. So when the 5G was introduced in the early 2000, they were desperately looking for the new filter. But the filter is made of aluminum nitride. So they approached us, can you manipulate the atoms in the aluminum nitride materials, which can swing the frequency from 6 megahertz to 20 megahertz. So we did demonstrate how you can manipulate the atoms in the atomic level, which resulted in a huge filter, which we commercialized through our Singapore collaborators. So then we went back and looked, okay, what can we do for New Zealand benefit? Because at the end of the day, we are a strongly applied science community. So then we looked at the catalytic surfaces, because catalysis play a major role in battery, hydrogen, and many energy applications. So then we come up with ion beams to make these catalytic surfaces at the insulator again. This case is a tungsten carbide and molybdenum carbide. We are able to manipulate the atomic crystal structure and create a new functionality either for battery or for hydrogen. But all these things done in a high vacuum, which is pressure below 1/1000th of time. But this is just shows you examples of some of our high impact applications which end up in a cover page where we first time demonstrated how piezoelectricity can be improved for 5G communication. Then I was invited to Cambridge, where the Rutherford discovery made in 2019 to introduce this whole concept of surface modification using ion beam, which then we also continued on making some prototype device for thermoelectricity. Then we looked at it, the climate change problem. Every world is looking for zero carbon energy carrier. We thought, okay, what can we do that? So then we identified catalysis play a major role in hydrogen production, which is the only zero carbon carrier at the moment. So you need a tiny bit of catalysis, because when you split the water into hydrogen to oxygen, you actually interact with the surface of the material. So we manipulated the surface of the materials to create a new technology for hydrogen production. As a result, we developed the world's first hydrogen characterization lab in Gracefield, where we can look at the people can look at the purity of hydrogen. That didn't stop me much, because like I said earlier, ion beams are used in a high vacuum conditions. That's why ion beam technology is highly controllable technology, which is used in microelectronics. Every IC, integrated chip, used in your computer, cell phone, it's all ion implanted. But New Zealand is not microelectronics. So we have been always challenging, can we do something for New Zealand? So what we did is we developed a small portable systems where ion beams can be used for coating. This is basically simply putting 20 kilowatt argon beam in a material, you sputter, you deposit in a substrate, which can create a new functionality, for example, wear resistance, corrosion resistance, bacterial prevention, and so many applications. Which way we have demonstrated someone in a medium to small scale industries in New Zealand can use technology for their product portfolio. But that did not stop, because whenever we interact with industry, they always say, John, it's great, but New Zealand is not a high-tech industry. Can you do something? What we did is we looked at some of the fundamentals of these ion beam technologies. then we come up with the world first, how we can travel the ion beam in air. So we are able to develop a technology called real-to-real ion beams, where you can assume the conveyor belt goes in, the ion beam comes in the air and modifies the surface, and which we have commercialized it. Recently, there is a company called B-Speckle, which came out of using real-to-real ion beams for hydrogen applications. Of course, I have to acknowledge the group. I got fantastic PhD students. When I started the group, as I said, I got 3 people. Now I'm leading 25 people, which means I got 8 PhD students, almost 20 postgraduate, who helped us to support this journey. And some of them joined us, the team, and we are continuing our journey. And thanks to our funding agencies, and thank you to my family for patiently supporting. Thank you.
Well, that was a good high energy talk. Thank you very much. Anybody got any questions?
Yeah.
When you're trying to get specific properties from a material using the ion beams, what do you change? Do you change the number of...
You change the number of atoms, where the atoms are located, and which crystal lattice it goes in. So that's what we do. We basically manipulate the crystal structure of the atom.
Okay, John, so ion beams. What's next? Neutrons? What are you going to do with them?
Now, we can still do a lot of the ion beams, as I said, even though we are the first people who patented the ion beam modification of materials to make nanostructures. In 2011, I have been granted a US patent where you can demonstrate this thing. But now, we started a journey to get the ion beam in the real world. This is going to revolutionize a lot of new applications. I hope my fellow colleagues will continue this journey, take it to the next level. Everybody can use it one day for many applications. Yes, that's Charles.
So one of your applications is ion beams to increase the surface hardness
Yep.
of metals. How much change can you make in surface hardness, and how wear resistant is that surface?
So we have demonstrated that if we can implant iron to micrometer, we can easily change the order of magnitude hardness.
Right.
Yeah. So we have done a lot of work on stainless steels. My previous collaborator, Ian Brown, ran a huge program on titanium, where we worked on a lot of work on titanium to change some of these functional properties.